There's a few different types of water monitoring that we'll implement here in New Jersey and across the world. They kind of span this spectrum from visual and habitat monitoring through biological to chemical on the other side. And so why do we have this divided out this way? On one end of the spectrum, the visual and habitat assessment, just looking at a stream can tell us a lot about the conditions in that stream, in that water body. So looking at these two images next to each other, you might be able to kind of identify some key features. The stream in the bottom image, we have a pool in the foreground. We've got lots of vegetation next to the stream. Um, we have kind of this variety of different habitats in the benthic substrate there. In that top image, we can see we have a lot of erosion, where the bottom stream we have kind of rocks mixed with pools and all of these different microhabitats. This situation on the top, we've had so much erosion that it's kind of smothered the benthic substrate on the bottom of the stream, so it's very uniform. So really, a lot of what we'll be looking for when we do our visual assessments will be to look for diversity. We want to find all the different ways that these different macroinvertebrates can exist in the stream and all of the different places where we have, biogeochemical reactions that need to happen for water quality. So on the other end of the spectrum, there's chemical monitoring. I do lump bacterial monitoring into this because we kind of sometimes will treat it in the same way that we do chemical monitoring. But the reason I lump it together is because this tends to be more of a snapshot, a single point in time. We go out, you can use a Lamat kit like you see here. You can use a handheld meter. Some groups have continuous monitoring sensors installed in the water, and they just kind of by 4G send that data to your computer. It's wonderful. You can even send your data out to a certified lab. But in all of these cases, what you're doing is you're going out into your stream, you're taking a sample, and you're trying to determine what the water chemistry looks like at that point in time. So dissolved oxygen is something that is definitely not static. You could go out to the pollen scale now, take a DO measurement, go out in the middle of the night, it will be different. To go out tomorrow morning, it'll be different. If you go out and the sun is beating down on the water, it'll be different. And so these values will continue to shift just as, from day to night, seasonally, but also as we have potential inputs of pollutants into our stream. But sometimes if you have this pollutant input coming into your stream and you're not there at the right time to catch it with chemical monitoring, it's hard for us to be able to quantify that and to document it, to be able to then fix that problem. The biology is kind of what ties together the visual and habitat and the chemical monitoring. So rather than look at a single snapshot in time, we're looking at the biology because it has to exist in that stream for a longer period of time. So it tells us a little bit more about the long-term trends in this stream. So when we're talking about biological monitoring for this program specifically in Stream School, we'll be monitoring for benthic macroinvertebrates. So what does that mean? Benthic means that these organisms live in and around the bottom of the stream. Macro means that they're large enough to see with the human eye, without a microscope. That doesn't mean that there aren't features that you might need a microscope to see more clearly, but the organism itself will be large enough for you to see. And invertebrates means that these are organisms without a backbone. So what does that include? Insect larvae, leeches, worms, crayfish, snails, clams. What does it not include? Things like salamanders, frogs, or fish. They all have backbones. So we would not count them in our sample, but if you do find an organism like that, it would be great to document that on your data sheet just so we know that there's some other life kind of happening at your stream. So why do we focus on macroinvertebrates specifically? Like I mentioned, they live in the stream for a longer period of time. So it could be anywhere from a few weeks, a few months, all the way up to a few years. And so everything that happens to that stream while they're living underwater is going to impact that population. They're also stationary. They don't move around a whole lot. So when we assess their population, we know that we're assessing this kind of local potential input and stream condition. They're easy to collect, as you will find, and they're also used as indicator species. This is perhaps the most important feature of the macroinvertebrate. We have assigned numerical values to each of these taxa of macroinvertebrate, anywhere from 0 to 10. So a pollution tolerance value of 0 means that you can handle very, very little pollution. So a stonefly, a mayfly, a caddisfly, these are organisms that have that low pollution tolerance value. They're very sensitive. And that means if you've had a situation, whether that's an influx of sediment or the pH has dropped or whatever the condition is, you will not find these very sensitive organisms. So these are the guys that we're really looking for. If we find the very sensitive organisms, we can kind of infer that we're doing okay and they have been able to survive. We also have some that are relatively pollution neutral. So on that scale from 0 to 10, these would be kind of in your 4 to 6 range. Yeah, they can handle a little bit of pollution, but when it gets real bad, then these guys will start to die off. And they include things like your dragonflies, your damselflies, and your crayfish. Now, on the other end of the spectrum, we have our very tolerant macroinvertebrates. These are kind of at the highest end of our pollution tolerance scale, anywhere from 8 to 10. They can live anywhere. These are things like scuds and worms and leeches. My favorite story about this is when I do macroinvertebrate collection, we'll preserve it with ethanol in the field so that we can bring it back to our lab to sort through with microscopes, and it's, we kind of catch a little bit more, we can identify them to a lower taxa. One time we did this, we preserved our sample in ethanol, we brought it back to the lab, and 2 days later, an aquatic worm was still alive in 95% ethanol. Now that is a very tolerant organism. So sometimes we think about these organisms and we're like, oh, we don't want those scuds, we don't want those leeches or worms. When these are the guys that are keeping our streams alive in our super polluted areas of the state. So I would like to stop and give a round of thanks to all the leeches here in New Jersey. Thank you for your service. We should want to find these tolerant species just as much as we should want to find the sensitive species. Because again, it's that diversity that we're looking for. We want to see bugs across this whole spectrum. So when we look at insects, there is a life cycle, clearly. A part of that life cycle will take place underwater. As we are doing a stream assessment, that is the part of the life cycle that we'll focus on. So this is a look at the black fly, for example. We have the adult. We're probably familiar with what the adult black fly looks like. I've been to the Jersey Shore, my goodness. And black flies, they lay their eggs in water, then they hatch, and they exist as larvae underwater. So in this juvenile phase, they'll kind of start small and grow and grow and grow and grow. When they reach a certain stage, then they'll pupate and kind of come to the side of the edge of the stream, pupate, and that's when they'll come out and hatch as an adult and fly away. So we focus on the larval phase here. That was the complete insect life cycle. So, a lot of times we'll talk about like the butterfly life cycle in our programs. We have an event called the Butterfly Festival. We focus a lot on this, where it goes from egg, larva, pupa to adult. There's also a group of insects that have what we call an incomplete life cycle. So they skip the pupa phase altogether. They go directly from the egg to the nymph, and then they grow and grow and grow underwater, and they emerge next to the stream, come out of the stream as adults. So in this GIF, I hope that it's playing for you. You can see an adult sitting on the surface of the water there, laying eggs. The eggs are dropping into the water. And you can see the eggs are still coming out. They're still kind of floating down. And even as she's laying these eggs, the eggs are immediately hatching underwater. And you can kind of imagine why that's necessary for a macroinvertebrate. Living underwater, you've got all these fish around, especially for mayflies, which is what we're looking at here. In May, and we're kind of at that point now, these mayflies will all hatch at the same time. And it's just like a fog of mayflies flying around a stream. And you literally are like doing this when you're walking around. But it only lasts for 12 hours. These guys spend up to 3 years underwater. They hatch, they come out. This is what that looks like. One of those emergers coming to the side of the stream and just crawling right out as an adult. And then it can hang next to the stream and let those wings kind of harden and fly away. So with the mayflies, with all insects that have an incomplete life cycle, we are focused on the nymphal and emerger stage. There's a great deal of variety in the sizes of organisms that we'll see. So if we look back to this image where we see the eggs, they're hatching immediately. Look how small they are in comparison to that adult on top. We can see insects anywhere along that scale. So there's a great diversity in size and also just how they look as they move from phase to phase. We have a lot of non-insects as well that we'll find, things like worms and leeches, snails and clams, and the crustaceans. That could be scuds, sow bugs, and crayfish. So looking at a crayfish, for example, their life cycle, of course, we have the adults that lay eggs, they hatch, and they kind of move through several instars underwater. And with crayfish, as their soft tissue grows, they'll shed their exoskeleton underwater and just grow a whole new one. And that's how they grow from each instar to instar. One instar is kind of one exoskeleton. They grow and they shed it and they move up and they move up and they move up. And so this is another example of just the diversity of sizes that we can see in the same category. One crayfish we could find looking very, very different. So just an introduction to working in a stream. When we are looking for a stream site, the first thing we want to do is we want to make sure that we have safe parking and we want to have a safe access point in the stream. A clay hill that gets really muddy. I've done a lot of slip and slides down these hills. So you just want to make sure that it's safe and that you feel comfortable going down into the stream. The stream itself, you want to make sure you've got sufficient depth. That means sufficient water for the macroinvertebrates to be able to set up shop there, and enough flow. And you want also a diversity of habitat types. We'll talk about that in a minute. The next thing is you want to have a defined 100-meter reach. So when we're looking at a stream site, when we go out to do an assessment, the first thing that we'll do is measure out 100 meters. That's going to be the framework within which we do our habitat assessment. We'll collect our bugs. We want to make sure that we have a defined start and end point. Now, and as I mentioned before, those stream sites, you don't have to, pick those on your own. Your program leaders from Foodshed and Sauerland will kind of assign those to you depending on, what your specific situation is. Or, some groups will use their volunteers to go out and try to find some new sites. And we have data sheets for that as well. We call that a site recon or site reconnaissance. Where you're looking for all these things: parking, access, flow, and also property ownership. Of course, you don't want to trespass on someone's property, but public property is always okay. And just with this picture, you can see it's also nice to have nice little boulders that you can sit on throughout the stream while you're doing your assessment. That's always nice. So streamside safety. You want to make sure that you're monitoring with at least one other person. If you kind of fall into the water and you're floating away, it's nice to have someone to wave to. and say, call 911. You also want to make sure that you're remaining aware of the conditions in the field. So that's wildlife, or vegetation. This image here on the left, this is of poison ivy. That's a big one, of course. But the image below this is Technu, and they don't pay me or anything, but I will do anything for this company. This is a shower scrub, and literally every time I come back from the field, I'll just use this shower scrub when I get in the shower, and I don't have to worry about it. The urushiol oils come right off, and you can just kind of move on with your life. Also, if it's hunting season, you want to make sure that you're remaining visible. So a high-vis vest, a high-vis hat, shirt, just don't wear camo, I guess, in the fields. You are hunting for bugs, I guess. But you also want to remain aware of weather conditions. This is a big one, especially in the springtime. So I've included a link here to the New Jersey Water Science Center. This is the USGS site. And they have gauges all around the state that show you kind of current conditions of stream flow. I checked this out at 2 p.m. today, and it looks like we've got a lot of streams in our area that are pretty higher than normal right now. And we're just crossing our fingers that everything drops down a little bit more before our first training on Saturday. I don't think we have a whole lot of rain in the forecast from now to then, so crossing our fingers. Another thing to consider at your site is the concept of decontamination to invasive species. Invasive species are everywhere. They're terrestrial as well as in the water. So anytime that we go into a water body, we want to pretend, we want to act like there's invasive species in that water. It could be anything like the New Zealand mud snail, which is currently in the Musconetcong River, and we'd like it to stay there. There's hydrilla, which took over the DNR Canal in recent years. Water chestnut, there's Didymosphenia, also called rock snot. There's all kinds of things that can kind of latch onto you and travel with you to another stream site. So what can we do about this? There's a 3-step method. First, you check your gear, you pull off any actual, bits of leaves and twigs, pull off everything you can, and then you clean it, and then you dry it. When we clean it, we have a packet of Alkanox. This is a biodegradable lab detergent that we'll have in the field. We can just kind of rip it open, put it into a bucket with the stream water, which seems weird to decontaminate from the stream water with the stream water. But we add enough detergent to get it soapy so that we can break apart those cell walls. So whenever you're in doubt, do I have enough Alkanox in here? Add another packet. You really want to make sure that you're cleaning off your boots, and you'll have scrub brushes and things like this too. So talking about finding the macroinvertebrates, we'll go over some basics about stream habitat and macroinvertebrate habitat, so that kind of provides some context for the next few nights. The first thing we'll talk about is stream morphology. And this is, we kind of look between 3 different morphological types in a stream. So this graphic here, we're looking at the side view of a stream, and it's moving past us, and we can see that in a pool, it's deeper. This is an erosional area. We have these larger bits of sediment that are being moved downstream. We tend to have finer sediment like, silt and sand at the bottom of our pools. It's slower. As we move into riffles, this is an area that's more shallow. We have more rocks, more cobble. A cobble is a type of rock that's sized. It's larger than gravel and smaller than like 10 inches across on the largest side. Then it becomes a boulder. So cobble is like between gravel and boulder. The cobble makes up the bed of the riffle. And as the water moves, it hits this cobble. There's all these bits kind of sticking out. and it allows the water to engage with the air to introduce some oxygen into that water. And that makes riffles a super productive habitat. Macroinvertebrates love oxygen, especially when it's dissolved. And so they'll hang out in these riffle areas. And so this is a look just from the top down. We can see the pools, it's a little bit deeper, the riffles, we have the rocks and the movement. It kind of looks like rapids on the surface of the water. A run or a glide, we call it a run, is the section of stream that kind of connects your riffles and your pools. So it's an area that's moving, but it's not necessarily so shallow with cobble that we have that like rapid action happening on top. So it's just a moving section of stream. The pools are going to be where there's not a whole lot of movement, or the water could even be kind of going in an eddy where it's even moving backwards. So here is a GIF so we can look at these three different situations. In the foreground, we have the water moving from the right all the way to the left. So we can see that movement. This is our run. We don't have rocks kind of blocking this area. So the water's just moving. After that, the water hits that left side of the stream and keeps going. And that means that we have a section that has been allowed to kind of slow down and churn. And that is that pool. And pools tend to happen on the sides of streams where things are a little bit slower. And then in the background there, we kind of go over this rock or log and we head into the riffle area. So just to summarize where we might find these macroinvertebrates, cobble and riffles, definitely a big one. Looking for submerged aquatic vegetation, another big one. We've got this damselfly hanging on to this bit of plant. Snags or submerged woody debris. So snags is just, it just refers to bits of wood that have kind of, branches or get kind of stuck together and they snag literally in the stream. And it kind of slows the water down behind it and provides a really nice place for those macroinvertebrates to hang out and get some relief from the flow of the stream. Or vegetated bank margins. So even if you don't have aquatic vegetation, meaning vegetation growing from the benthic substrate of that stream, we could have terrestrial vegetation on the side, just kind of hanging into the stream and providing places for those bugs to just cling onto. So the terrestrial vegetation is also important. So we'll take a closer look at cobble and riffles. We can see the water is moving. It's very shallow. We've got lots of rocks and cobble. And when we flip over one of those rocks, this image on the right, we can see we've got some macroinvertebrates that have set up shop. These are caddisfly larvae that create their own cases out of bits of sand grain or bits of plant or twig, and they just wrap it around themselves, and it provides a nice little cocoon for them to live inside. And they produce a silk underwater. They can attach themselves to the bottom of rocks. So I hope that every time we flip over a rock, we see something. Maybe not caddisflies. It could be a mayfly scurrying away from you. It could be a water penny that's just hanging out. But under these rocks, there's a whole world happening. And that's what we're after. The logs and woody debris, also a really great place. So this is a look at those snags. You can see it's the small bits of twigs that have just been blocked by this bit of log. And we get a lot of calls from people when they see things like this, when they see logs jammed in a stream, they'll say, how do we get this out of here? We need to clear the flow. And I say, no, don't do it. Because we love to see the diversity. We want to see that flow broken up however we can. This video I took in South Jersey, so it's logs and vegetation play perhaps a bigger role in South Jersey. In North Jersey, we might create these little spaces with boulders, anything to kind of put in the middle of the stream and create these slow spaces are really important. Next, aquatic vegetation. And again, this is vegetation that comes from the water and lives in the water. Sometimes it can get a little bit confusing towards the edge of the stream if you're like, is this terrestrial? Is this aquatic? So for our purposes, you're just looking for bugs. I think if you're questioning it, you could sample it, look for the bugs, see if they're there in either case. But here's a few different types of aquatic vegetation. Debbie will go over this in greater detail tomorrow. So looking at these types of habitats, let's compare that to the different types of ways that macroinvertebrates move and live. We call this their locomotion. So looking at riffles, we have a lot of these clingers and crawlers. Clingers are those that can kind of suck, like adhere themselves onto a rock so that they can stay there. And imagine this always constantly moving system, this stream that's always flowing. What you want to do as a macroinvertebrate is you want to figure out how to kind of stay in one place. You don't want to be just tumbling, with the water and end up in the ocean, eventually. So clingers literally cling onto rocks. Crawlers are the guys, they're like mayfly larvae. They've got these really buff arms and they tend to be kind of flattened, streamlined, so that they can crawl over these rocks and not get swept away with the water. Climbers are those that hang on to vegetation. So we saw an image of a damselfly larva a few slides ago that was just kind of clinging onto some vegetation. Those are climbers. Swimmers, we are those that are adapted to swim and they can literally move around all they want around the water column. Sprawlers are those lazy guys that hang out in the bottom of pools. They lounge on the stream bottom. So think of like a crayfish. They're just kind of hanging out there. And then burrowers are those that dig down into the sediment. So you can imagine something like a clam that will get down in there and just kind of wiggle its way down. So with all of these macroinvertebrates, all of the different places that they live, it's important for us to keep that in mind when we're out in our stream. We want to, again, sample the whole diversity of these guys. So we want to make sure that we hit these different habitats as well. Another way to frame how to look for macroinvertebrates, besides their movement and where we might find them, is how they feed. So as this is a water penny larva, you can kind of see it looks like a penny on the top. We're very creative when we come up with names. This is a grazer or scraper. And this is, in the last example, would be the clinger. So this is one that kind of sucks itself onto the rocks. And it's like a cow. It just walks over the rocks, munching up that biofilm. You can literally see the little trails of clean rock through biofilm as these guys hang out. There you will definitely find them in riffles. Shredders are another type of macroinvertebrate feeding group that is super important, especially in our headwaters, our smaller streams where we have more interaction with trees. So where we have a lot of leaf fall in the stream, that's a lot of carbon that like, how do we manage that? The shredders are doing a huge ecosystem service for us. So this guy, this is a stonefly nymph, and he's just munching away at a leaf. And what he's doing is he's turning this, what we call coarse particulate organic matter, larger bits of organic matter like leaves, and he's pooping it out and he's turning it into fine particulate organic matter. And so this FPOM, this fine matter, this is what is required for other types of macroinvertebrates. Other types can't, they just don't have the munchers to work on these larger bits of carbon. And so this guy does that job, makes them smaller for everyone else. So as you might imagine, you might find this guy in a leaf pack. Another type are collectors. So collectors we break up into two different groups. We have those that filter small particles from the water. On the top, this is a black fly larva. And I don't know why, I just love them because what they do, they have a sticky butt. They stick their butt to the bottom of the stream. Do you see these big, beautiful fan-like mouth parts? What they'll do is they'll just take those mouth parts, stick them up into the water column, and as fine particulates come out, stonefly poop, we might call it, they come and they grab it and they're like, okay, Just mention. And they hang out in these very dense, like forests of black flies at certain times of year, literally where you're walking across the rocks and you're slipping and you think it's algae. You look down and it's just black flies as far as the eye can see. Not this time of year. I don't think we'll unfortunately, I don't think we'll see that, but earlier, like February, March, that tends to happen. Another way that these collectors work is by gathering. In this net, this is a net spinning caddisfly. People have been trying to recreate this underwater silk for so long because it's actually, how do we get it to be like waterproof and sticky underwater? It's kind of amazing. These net spinning caddisflies, they'll spin these nets and just hang out inside. It's a little bit more passive. The fine particulates come flowing down and they can eat their food. So another type are the predators. And I just show this GIF because it's like, come on. This is a dragonfly nymph, that has a lower jaw it can extend out, grab prey, and bring it back in to eat. What a super duper adaptation. But these predators, they're usually free swimming, so you can kind of find a predator, maybe in any sample you might take. Be careful if you have them in your tray, in your sample with smaller organisms, because you might start to find that your numbers dwindle as you create a little lunch for these guys. All right, so we'll talk a little bit about sampling now. I have a link here to a YouTube video. You'll get these slides if you would like to. You can check this video out. I just think it's a nice, quick introduction to sampling in general. So when we actually go out to sample, what do? Pick our 100-meter stretch, our furthest downstream point, our furthest upstream point. And our goal is within that 100-meter stretch to take 10 to 20 samples from the most productive habitat. We want to hit all the different habitats within that 100-meter stretch, but we want to focus our efforts where we'll actually find the bugs. So here's a little upside down triangle showing the most productive habitats at the top. Riffles we would like to prioritize, and then woody debris and vegetation after that, undercut banks after that, and then sediment. We don't really find a whole lot of bugs down there, but we still do find some. So we do want to focus some of our effort there. And ideally, we want to start at the furthest downstream end of our stream and work our way up, because as you'll see, in the process of sampling, we're disturbing the bottom of the stream. And so we start downstream and then we move up. If we started upstream, that sediment would be kind of moving downstream and possibly affecting our future samples. So we start downstream, move up. That's fine. Now, sampling in a riffle, I'm going to go through just the steps here. I think it's helpful to just see the images before we actually get out in the field, so you can kind of start wrapping your mind around it. We use a D-net. This is a net that has a flat bottom and rounded top, so it looks like a capital D. You put that flat bottom at the bottom of the stream level. Then within a 1 square foot section in front of that net, like this video is showing, you'll pick up the rocks and scrub them into the net. You want to make sure that anybody that's clinging onto those rocks, you really got to scrape them off into the net. These guys are adapted to cling, so you may need to be a little bit rough with those rocks to get them into the net. Once you clear the area of larger rocks that you can pick up, then you're going to kick your feet down into that 1 square foot section in front of the net. Now your net's going to be facing upstream, so the water is going to be flowing into your net always. So as you're kicking down into the sediment, the idea is that you're dislodging the organisms there. They come up in the water column and they move with the flow into the net. So we're not necessarily kicking into the net. We're just kicking down, disturbing as deep as we can go, maybe 6 inches down. Kick for 45 seconds to a minute. We kind of call it the macro dance. We'll get very proficient at it at the field day, and our sample will end up in our net. So that was the procedure for riffles. We have a different procedure for vegetation and woody debris. Now, let's see if we can play that. In the woody debris on the right, we have someone who's found this wonderful log, and basically what they're doing is they're sticking their net underneath and scraping the bottom of the log. So it's kind of the same idea. Things are clinging or hanging in those interstitial spaces of the wood. We just want to scrape that log really well, get everything into the net. For softer vegetation, what you could do is kind of jab at the vegetation, massage it with your hands, like literally into your net, get everything off of there. Or you could sweep through the vegetation. It kind of depends on the type that you're working with. But once you have your sample, whether it's wood or vegetation or a riffle, you're going to take your net after each of those samples and empty it into a bucket, rinse your net into your bucket. And then you go back out and you repeat. So you want to get, each one of those is one sample. You want to get 10 to 20 samples throughout your reach. Mixing it up between the different habitats again, but focusing on the most productive. Once we have our 10 to 20 samples in the bucket, then we will do subsampling and identification. So we basically take out food containers, and we'll swirl it around in the bottom of the bucket, bring it up, and that is our subsample. It could be that there's literally thousands of bugs in your bucket, and I don't have the time for that. You guys don't have the time for that. That's why we're subsampling, trying to reduce the number that we're actually identifying. So we sort it into these ice cube trays and then use dichotomous keys like the like the image on the right to make those identifications. Then we use our tally sheet. This is our macroinvertebrate tally sheet that we use here specifically in New Jersey. We break it out into, I think it's 22 different taxa. Excuse me, sir. And this is the master list that you'll be working with. This is not an exhaustive list of all of the different macroinvertebrates you could possibly find. This is just the organisms that we're targeting for this particular project. So it could be that you find other bugs, and unfortunately, they just wouldn't count in this method. But again, you could record that on the data sheet and just let us know kind of other things that you're finding if you do find other taxa. Now, the data sheets, when you're finished, you'll send that to your monitoring group captain, whether that's Christine or Robert. And then what happens? So here in New Jersey, we're broken out into a few different provinces. We've got kind of a high gradient area in the northwest, and we have the coastal plain in the southeast. The bugs that we find in these respective areas will be different, and that's totally okay. And we want to assess them differently because a healthy stream in each of these areas will look different. So in New Jersey, we've established 3 different ways to assess a macroinvertebrate population. You're aiming to identify at least 100 organisms stream side. You mark those on your tally sheet. When we get that data, we'll then use one of these indices. I realize that this is small, and so this is something you can kind of come back to later if you're interested in like literally how it's calculated. But we'll look at things like the total number of taxa, how many of those bugs are sensitive, the average pollution tolerance value. If you've got a lot of clingers, the percent non-insects, all of these things come together to calculate a total score from 0 to 100. That's broken down into 4 categories: excellent, good, fair, poor. So your collection will be turned into this score, this rating, and that is how we report it to DEP, and that's how it kind of ends up in the integrated report that Debbie was talking about earlier. So with both of your groups, we'll submit your data to the Water Quality Exchange. This is the EPA national database. And then that's pushed through to DEP, that they pull that data, and they look at this in also with your habitat assessment results, which also come back as excellent good fair poor.